So 4.2a is the mean value theorem. So the mean value theorem basically only applies if the function is continuous at every point over the interval. So do you guys know the difference between the square brackets and the curved parentheses, what they mean? Included versus not included, right? So, if it's continuous over every point on the interval, so there's no discontinuity, like a jump, a point discontinuity, or a vertical tangent, okay? Then, we want to check for differentiability. If it's differentiable on every point over the interval that's in the interior, okay? So interior means we don't need these 2 points to be differentiable, only everything between them has to be differentiable, okay? Does that make sense? So the endpoints only need to be continuous, everything else needs to be continuous and differentiable. If all of those things are true, then it's true that there must be at least one point, we call it C, in the interval where within that open interval where the instantaneous rate of change equals the average rate of change. So you guys remember instantaneous versus average rate of change when we learned about secant lines versus tangent lines? Okay, good. So a tangent line is where you take the derivative and you plug that value in at x and you get the exact slope, which will always look like a tangent line. It touches one time and never touches again, right? A secant line is where you connect any 2 points, you find the slope of that line, and that's the average rate of change, or the slope over that line. That's like taking the slope like you learned in Algebra 1, y2 minus y1 over x2 minus x1. So it's saying that there's a point, every single time mean value theorem holds and applies, there must be at least one tangent line that matches the secant line. Does that make sense? The slopes match. Do you guys see how the slopes match? Okay, so that's the theoretical understanding of the mean value theorem. Okay, that's the idea. So here's the algebra side of it. You take the derivative of the function and you set it equal to the slope if you were to calculate the slope. Okay, so let's go ahead and try it out with an application problem. All right. So step 1 is we have to first confirm that it's continuous and differentiable. So you can kind of see a picture of this. Is it continuous over this interval, this function?
Yeah.
Yes, there's no breaks in the graph, any type of discontinuity, right? If you put your finger down on one end, you can not pick your finger back up to get to the other side, okay? That's continuity. And we also know that this is a quadratic. We know quadratics are continuous anyway, so you didn't need the picture. Differentiable. So it only has to be differentiable from here to here. It doesn't have to be differentiable at the endpoints. That's important. So what do you guys think? Is it differentiable?
Yes.
Yep, it's both. So once you've said yes to both of those things, you can proceed to the next step. The next step is to take the derivative of the function. So what would be the derivative of this function? 2x. Step 2 is to find the slope over the interval given. So in this case, I gave you both the coordinates, but what if I only gave you the 0 and the 2? What would you do to get the y values? Plug them into the function. Good, so oftentimes you're only going to be given the x values. You have to plug them back into the function to get the y. So like 0 squared is 0, 2 squared is 4, and now I have the 2 coordinates. Okay? Then you're going to calculate the slope, y2 minus y1 over x2 minus x1, which gives me m equals what? 2. Now you're going to set mt equal to ms. So mt represents the slope via the tangent line. That's what that means. And ms is the slope via the secant line, which is the average rate of change. Because remember, tangent lines represent instantaneous rate of change, secant lines represent average rate of change. So they're telling you to set the derivative equal to the slope. And then you solve for x, and x is what?
1.
Good. That's what we call our c value. Okay? So a c value is always representative of the x value. Okay? Now, of course, if you want to know where the c value occurs exactly, you could plug the x back into the function to get a coordinate, right? It would be at 1, 1, which would be right here. So what this means in theory is if I were to draw a tangent line at this point, which would look something like this, it's not going to be exact because I'm just eyeballing it here, by the way. So it's going to look something like this, the tangent line. Everybody understand that? The secant line occurs when you connect the 2 endpoints that you found the slope with, right? So I use these 2 points to find the slope. That means that these slopes should match according to MBT, and you can see they do. Of course, I know it's not exact, it's just a sketch. But yes, this is what we're proving here. That's the reasoning behind what we just did. Okay? Alright, so that was a nice simple example. We're going to look at ones that are a little more complex. So this one here, first thing we got to figure out, is this function continuous over the interval? Thank you.
Yeah.
Yeah, there's no breaks or any of any type. Is it differentiable over the interval?
No.
Thanks. You can grab a note. It's right there. It is. So here's where you have to be careful. Yeah, it's continuous, but it's not differentiable. Why is it not differentiable?
Cusp.
It's got a cusp in it, right? So right here we have a cusp, so we can say that this doesn't hold. So we would see MVT doesn't hold. So if MVT doesn't hold, you can't find a C value. So let's say you totally forgot to check if it was continuous differentiable. You jump right into taking the derivative, setting it equal to the slope. You forget. The good news is the math will not work out. So if you accidentally just start doing the algebra, it's going to be impossible. You're going to get an extraneous solution. You're going to get like over 0, or you're going to get something that just will not mathematically work out. So just be aware that if you miss that step, it will not work. So yeah, you got backup. Okay. All right. Next one. Remember, we're looking from 0 to 8. Okay, so you have to look at the interval because some functions are continuous and differentiable over certain intervals, but not over others, right? So, is this function continuous over this interval?
Yeah.
Now, here's where you have to be careful. Remember, it only needs to be differentiable on the interior. The endpoints don't matter. So, as you can see, it is not differentiable here, right? But does that matter? No, it only needs to be differentiable on the interior. So the answer is yes, it's differentiable where we need it to be differentiable. So, step 1 is going to be to take the derivative of this. That's 3 times 2 over 3 times x to the power of negative 1/3. Remember, you subtract 1.
We had this exact one.
Yeah, in a different problem. And then we get 2 over x to the 1/3 power.
Okay, yeah.
So, here is where we have an example where they give us one of the coordinates. But how can I find the other coordinate? Plugging it in. So if I plug this in, this is where your algebra skills have to come out. This is the same thing as the 3rd root of 8 to the 2nd power, which is the 3rd root of 64. Anybody know what the 3rd root of 64 is?
4.
What's 4 times 3?
12.
So it's 12. So now that we have the 2 points, we can find the slope. I'm going to do it here so I have room. Y minus y over x minus x. What is 12 over 8 reduced to?
2 over 6? Or, wait, I'm crazy, aren't I?
3 over
3 over 2.
3 over 2, good. So once you find the slope, you can set it equal to the derivative. And then to solve this, we can just cross multiply. So we get 4 equals 3 times x to the 1/3, divide by 3. Now, I don't know if you guys remember this or not, but in order to get rid of a fractional exponent, anybody remember what to do? Put it to the reciprocal power. Yeah, 3rd power, exactly. On both sides, of course. So x is equal to 64 over 27, because I got to put both of those numbers to the 3rd power. So that would be our C value. Now, it's really wise, if you're a wise student, okay, to check what this fraction is approximately. Why would that be useful to us? It's approximately 2.4. Why is that important that I check that?
I don't know.
If I would have gotten 23, what would have been the problem?
That's
Oh,
probably
it
way
wouldn't fit
too high.
in the restrictions.
It wouldn't fit in the restrictions. Yeah, the interval, yeah.
Yeah.
Essentially, so you want to be careful because we know that the C value has to be within this interval. If it's not within that interval, you know something went wrong, right? So always be able to check your work for your mistakes. Okay? Make sense? All right. Next one. So remember, looking at the picture here, because we're only looking at a little glimpse of it, what would be, would this be continuous?
Yeah.
Yes.
would it be also differentiable?
Yes.
Yeah, so the only time it's going to be continuous but not differentiable are cusp corners and vertical tangents.
Can we add the endpoints?
What?
Can we like add the endpoints since it's saying like where we're working from?
To make it visually easier.
Yeah.
Sure.
Okay.
Yeah.
See, like this one that has no point.
Oh,
endpoints.
yeah, you
It's
can.
between 2 and 4, so can I add that?
Yeah, of course. It's just not as precise as like plugging. We're gonna have to still plug it in, by the way. We can't estimate.
No, I'm just saying
Yeah,
visually. it's
I get what you're saying. Yeah, totally. Okay. So does everybody understand why it's continuous differentiable here? Now, when it's continuous but not differentiable, you're mainly looking for cusp corners and vertical tangents, and we know those occur when we have even over odd or odd over odd. Don't have any of that. So that's it. And then of course, if you have like a denominator, remember those are vertical tangents. It's been a while since you've done that, but just a reminder. So now we're going to take the derivative of this. If you remember, the derivative of ln of anything is 1 over whatever's inside times the derivative of the inside, which would be what? 1. So no need to write it. Now, of course, we have to find our coordinates because I only have the x values. Now, you can't, unfortunately, just plug these in. I think, now that I look at it, I think our graph might be off, so don't be too alarmed. I think it's like shifted 1 over. We talked about this the other day, and then I forgot to change it. So what you're going to do is you're going to plug these values into the function.
Who's we?
Me and a coworker.
That's not me.
So we get ln of 1. Anybody know what ln of 1 is? 0. For the next one, we get ln of 3, which if you put that in the calculator, it's a nasty decimal. Yeah, so we're going to leave it as ln of 3. Okay, we don't mess around with decimals in here like that. Hello? He's actually in Miss Patrick's room right now, finishing an assignment. You're welcome. Bye. All right. So, this right here would be ln of 3. So now we're going to find the slope. So it's going to be y minus y over x minus x, which of course ln of 3, we're just going to leave it as ln 3, so it's going to be ln of 3 over 2 is our slope. So now we take our function and set it equal to our slope. And then we're going to cross multiply. We get ln of 3 times x minus 1 equals 2. Divide both sides by ln of 3. Just a bunch of algebra. We get x minus 1 is equal to 2 over ln of 3, and then what's the last step?
Minus 1, or add the 1.
Add the 1. Like so.
So c equals 2 over ln 3 plus 1.
Correct. And it wouldn't be a bad idea to get a decimal approximation for that. It's about 2.8. What is that music? Oh. Okay.
I don't hear music. You're going crazy.
You guys definitely heard something.
You're going crazy.
I mean, maybe, but like there was still music. All right. So does anybody have any questions about that?
Nope.
The
Okay.
voice is in your head.
So the steps are basically the same, but it's just like more difficult math. All right. So your homework, you're going to have all class period tomorrow, but I would recommend working on it today and tomorrow so you don't have to do it at home.